Welcome to lecture 41 today. So we shall continue our discussion from the last lecture where we are talking about resurf in LDMOS, and today we shall finish our discussion on LDMOS, RF LDMOS, okay, because LDMOS can also be used for high voltage switching, but in this course we are talking about the RF performance of LDMOS, okay. So over to the slides here. So in the last lecture we talked about reduced surface effective field, by which you can actually increase the breakdown voltage while not sacrificing the on resistance, and that we discussed in details in the last lecture. So today we'll talk about hot carrier injection, and it's a very vast topic and it's a very important reliability concern. In this course, of course, we'll not go into much details because we are covering different topics of different device technologies, to a level where we can understand and appreciate the basics, okay. So what is hot carrier injection? The term hot carrier means that they are highly energetic carriers, and they can be observed, or they happen to happen, they can occur in the device at very high fields. So when I say very high field, I do not mean a field that will necessarily initiate avalanche breakdown, but even before avalanche breakdown the field can be sufficiently high between the gate drain region, right. In this region the field can be sufficiently high, and when the electrons are highly energetic, they are called hot electrons, and they can lead to reliability issues. So what happens is that very high or very highly energetic electrons, when they move, they can collide with other electrons, they can collide with phonons, they can collide with impurities, ions, etc., and they can get misdirected. So they are moving in the channel. So maybe I can use a different color here. They are going to move in the channel here, but they can collide with all this background electrons and other kinds of ions, etc., and they can get misdirected because they are highly energetic. They can enter the oxide in the below the gate. They can also enter the oxide in the drift region, okay, and that also there is another parasitic bipolar effect that I'll come to slightly later. But electrons that are highly energetic can have a tendency to be misdirected and enter the gate oxide, and they may enter the oxide above the drift region, okay. This primarily happens because of the high field that exists between the gate and the drain, and the peak of the electric field, as we have discussed in many cases, exists near the drain edge of the gate. Okay. Now depending on where these highly energetic electrons are injected, they might be injected in the oxide below the gate or below the oxide in the drift region. Two different consequences may happen, okay. Overall, the on current or the saturation current and the on resistance of the device are impacted by hot carrier injection, and that's why it's a major reliability concern, okay. So what happens is that if the electrons are injected in the oxide below the gate, then they will create additional negative charges in the oxide, okay, and they will reduce the depletion spread that is happening below in the channel. What happens is that it basically affects Vt. Your threshold voltage will shift by some amount delta Vth, okay, and the magnitude of course depends on stress levels, and it depends on the bias, depends on how much of hot electrons have injected, etc., but the major reliability concern for hot carrier injection in the oxide below the gate is a threshold voltage shift, which is undesirable, okay. And if the threshold voltage changes, of course for a given gate bias your on current might change because your overdrive will change, correct, the gate overdrive will change. If the electrons happen to be injected in the oxide above the drift region, then what happens is that because electrons are injected here, you will have equivalent positive charge in the drift region, which means the total electron concentration in the drift region will reduce, and that means your on resistance that is arising out of the drift region will increase, okay. It will increase because electrons have gone into the oxide, creating an equivalent positive charge in the drift region, which means the overall electron charge is reduced. And if your on resistance increases, then your current increases or current decreases. It's bad for your device, essentially what on resistance increase means that if you have your IDVD, you had a like that, but now after on resistance increase it might look something like that. So that's a new workout we call in 3.5 technology, but it's an on resistance increase, and that leads to a lower dynamic swing in the gate output voltage. So overall your power capability is reduced, your current is also reduced, current swing is also reduced, so you have reduced power capability. So hot carrier is a nuisance, it's a bad thing, but then you can prevent hot carrier injection by reducing the field between the gate and the drain, okay. This is the gate and the drain. So between the gate and the drain, if your field is reduced, then your hot carrier injection also will be reduced. But to reduce the field, what happens is that you have to increase the gate drain spacing, LGD. For a given drain bias, if your gate drain spacing is large, then your hot carrier injection will be reduced because your field will be low. But a larger LGD also will lead to a larger on resistance, which is bad, okay. So your hot carrier injection will trade off with on resistance, Okay, so it's a optimization problem between on resistance, on current, hot carrier injection. Okay, device dimension, power capability, all of this have to be co-optimized, otherwise we'll sacrifice one very much for the sake of something else. How do people quantify it? They will look at some parameter, say on current. How much is the on current reducing? So on the y-axis you can see the on current, on the x-axis you can see the time. It goes from 10 seconds to 1 billion seconds. Of course, you do not measure over 1 billion seconds. You measure up to something like 10 to the power 4 or some 10 to the power 5 seconds, okay? Somewhere between that, and you extrapolate. What do you do actually? You stress the device. You stress the device for, say, for instance, 16 to 48 hours. Just an example. You stress the device under DC condition. When you say stress, it could be you apply high field, you let the device see a very high field for a 16 to 48 hour duration. There are different bias conditions, semi-on, on, off-state condition, etc., etc. But you bias the device, and then over this duration, 10 to the power 4 to 10 to the power 5 seconds, you keep measuring intermittently the current or the threshold voltage. Okay, you may keep measuring the on resistance, you may keep measuring the on current, and then you will see that the on current keeps degrading with time. Initially, it will degrade very fast because it's a log scale. Remember, over time it will degrade very slow. Initial degradation is fast, and then it will degrade very slowly. Okay, so it looks linear because it's a log scale. Okay, so in the first few hours you will see most of the degradation, then it will just level off very gradually. So you measure the on current intermittently after every your time spacing of measurement has to be logarithmically varied also. So you keep measuring the time after a logarithmic interval of time, you keep measuring the on current, you keep measuring the on resistance, and we'll see that the on current keeps reducing because the device is subjected to a stress. And because of this electrical stress, you have hot carrier injection in the oxide, and because of that your current keeps reducing. And as you see the current keeps reducing, you measure till 10 to the power 4 or 10 to the power 5 in that range, and then you extrapolate in that as to what would be your degradation in the current over 20 years. So that's like your 20-year degradation. So the typical value at 20-year degradation, this should be less than 10% of your original value. I mean the overall degradation, the delta I that you're having should be less than 10%. Okay, the delta I reduction. That's a good measure that over 20 years your on current is going to reduce by less than 10%. That's a quantifying of one of the ways of quantifying hot carrier injection. Then comes, and this another reliability concern will come, there's a snapback, there's ruggedness. First, ruggedness. What is ruggedness? Ruggedness is a very unique thing. It's the ability of a device to withstand RF excursion. So you have RF swing, right? So different levels of mismatches. When I say mismatch, suppose you have an FET, okay? Suppose you have a transistor, I'm giving a symbol of a transistor, something like that, and then you are delivering power to some load, say ZL, impedance. Okay, now the output of the device has some output impedance, and the load to which you are delivering power is ZL. So typically you need an impedance match, of course, but if you have a mismatch between these two, and you will have a mismatch, what is the maximum amount of mismatch you can accommodate and still the device behaves acceptably? That's kind of a way ruggedness is validated. So at the output you intentionally present some mismatched condition, okay, or load. A mismatched load is presented at the output intentionally, and you see to what mismatch ratio your device behaves within the acceptable limits. So that's how people test for ruggedness. Okay, we are calling it at the level of RF voltage or current excursion. So the way they show it is basically a VSWR ratio, voltage wave standing ratio, or voltage standing wave ratio, and we'll talk about that when we discuss about the basic microwave concepts probably next week or next to next week. But essentially VSWR, it gives a ratio of the mismatch that you have between the incident wave and the reflected wave, and higher the VSWR ratio, more is the mismatch from the output side. So people qualify the devices at 1:3 or 1:5 or maybe 1:10 mismatch ratios between the device and the load, and higher the mismatch ratio in which you can define the device to be working acceptably, better is the device's ruggedness. Okay, so ruggedness can be defined or can be measured at different levels of VSWR. Okay, and of course you will have different levels of drain voltage, you can have different levels of overdrive, etc., etc. That's about ruggedness. Snapback is a little different concept. Snapback happens typically in silicon devices such as LDMOS. It's unusual or uncommon in 3.5 devices as much, because in silicon devices you have a parasitic BJT that forms actually. I'll come to that. Okay. Breakdown voltage is one thing. BVDSS is the breakdown voltage which you define in the off-state condition of the device. Your device is pinched off and you define the breakdown voltage. But in the RF operation, the device will see high voltage also, and high current also. So there is also a breakdown corresponding to on current, on state. Okay, so essentially both the off-state breakdown voltage and the on-state voltage are critical in designing the device and in really understanding how the device, the performance limits of the device. Okay. So whenever you have a voltage swing, you want that the voltage swing should not exceed the breakdown voltage, or even if it has to exceed the breakdown voltage, it should spend as little time as possible. Okay. Ideally, you want the breakdown to be very, very large, infinitely large, but then you cannot do that because you'll have to sacrifice your on resistance infinitely, which is not realistic. So within the given constraints, you want the breakdown voltage to be such that it just meets the criteria of all reliability, HCI, etc., and no more. You do not want that the voltage swing exceeding the breakdown should spend much time there. Okay. So now, what about a parasitic BJT I talked about, right? The snapback effect that we are talking about. So I'll first come to how a snapback looks like. This is how a snapback looks like. On the y-axis you have a current. It's a TLP. It's a transmission line pulse generated current. It's not like a DC sweep, because if you do a DC sweep, the device will be destructively burned down or destroyed. So you release the charges in like a pulse. Okay, so it's called a TLPG setup, where basically it's you have a transmission line and you can think of it as a metallic line. You charge it up to higher voltages, and then you use a switch to kind of release charges intermittently, so that you do not do a complete DC sweep. Otherwise, the device will completely burn down. So you can see that its off-state condition, for instance, the current is low. Suddenly the current will rise. This is where you are entering the breakdown, and suddenly the current will go in this direction because the device has undergone snapback. It means at very low voltages you will have very high current. That's why it has come back to this side. Now that is a consequence of having a parasitic BJT in the thing. Where is the parasitic BJT? Because the source is N-type, the drift region is N-type, whereas the body is P. So there's an NPN BJT here. This is the base emitter. The source side of the FET and the substrate, is like the base emitter junction. So what happens is that when you have high electric field and the carriers are about to or almost getting started with impact ionization, you will have sudden electrons and holes generated. This is the high field region. So you will have enough electrons and holes generated because of the start of avalanche or because of the start of an impact ionization. Okay. So what happens in that when you have a large number of electrons and holes in this region is that your electrons will be pulled out of the drain, but the holes will be injected to the base. Alright. The way you have this p-n junction and you are generating a very large number of electrons and holes, so holes will be fed into the drain or into the substrate here. Now it's like the holes are feeding into the base, correct? So because holes are feeding into the base, you can say that the emitter base junction is like a forward bias junction because the holes are being fed into the base. Okay, and because of this forward bias emitter base junction, more electrons will be injected from the source side, okay, and into the high field. This is the high field region. So more electrons will be injected from the source to the high field region. More the high field region experiences an energetic electron inflow, the more the electron hole pair creation will happen and more holes will go into the substrate, more forward biasing the p-n junction, resulting in a positive feedback like a runaway. It's like a current runaway, and the BJT will get more and more forward biased, and the more forward bias the BJT gets, the more current you inject to the high field region of the drain side, and more the BJT gets more forward biased. So this loop, the BJT getting forward biased, okay, and in turn releasing more electrons to the high field region. This happens like a positive feedback, and that positive feedback leads to this snapback effect here. It can suddenly happen when this feedback starts getting out of control. So it can lead to a catastrophic failure actually. That's why people do not do a DC sweep to measure it. Okay. To get better ruggedness, to get better device performance, you of course need to prevent snapback. So you need to ensure that your avalanche multiplication or impact ionization process starts delayed. Okay, and for that delay to happen, you can introduce some design approaches where the whole injection into the base is kind of minimized or it's kind of prevented, or the high field region you try to move it away from the parasitic BJT location with some device design so that you delay the onset of this avalanche multiplication, and hence you delay the offset or onset of this start of this parasitic BJT, the positive feedback that you have, okay, that you try to delay. Otherwise it will lead to snapback. And so everything is ultimately a question of optimization and trade-off. You want to optimize something better, you have to sacrifice some on resistance or something else. Okay. So as I told you, the way to reduce snapback is or to delay the snapback is to move the impact ionization location a bit away from the high field region by some you can engineer the field profile, the drain profile, the doping profile, etc. And that's how the snapback is. You cannot control snapback, but you just delay the onset. Like you want it to happen at a little later voltage, for instance. Okay. So that is all about snapback. And finally, we are here at the finger layout. You can see that this is actually a not a schematic. This is actually an image of a very high voltage LDMOS RF device, and you can see it's very long. I have discussed about the layout of such multi-finger devices in details when you talked about 3.5 devices. Things aren't much different here. You can see that each finger here is around 0.5 millimeter, actually 0.5 micron. This is 0.5 micron. Okay, each finger, and you can have hundreds of that. Okay, this dimension also matters. This dimension, whatever dimension you have said D, but it should be much less than say lambda by 10. I told you typically lambda by 100 or lambda by 200. It should be that overall distance. Otherwise, you will have phase delays and phase incoherence. Okay. So you have a mega drain pad here, and then there's a massive gate pad here. There is no source pad because the source is, as you know, the sinker is connecting the source to the ground directly. So there is no need for via holes also. You have a large area of fingers, and this device, for instance, is a 50 watt LDMOS, or 50 watt to 200 watt. So it can be, depending on the number of fingers, you can have few hundred watt. There are commercial devices that can go up to kilowatt at lower frequencies, sub 1 gigahertz. But there is a lot of engineering novelty, engineering understanding that goes in optimizing such a massive layout. First of all, your heat will be immense. So the thermal management is critical. How you cool down the device using heat sink or any other approaches. Packaging is very critical. How will you package the device? Okay, you need to have wire bonds from the gate, for instance, wire bonds from the drain on the manifold, on the package manifold, or probably on a fixture, on a board. If you want to package it, then it has to be package manifold. If you are not going to package it but just do a on-board demonstration of some amplifier or something, then you can just have it on a fixture, which is put on a board. You can have a RF substrate or a board on which you put. Okay, so you bring in RF signals to that a connector on the board, and then that you will feed it over to all this with multiple wires, because you need multiple wires, because you do not want at one wire to be feeding and there will be delay across as it propagates. So you want multiple wires feeding them intermittently, and this wires length and dimension also matters a lot, by the way, of this wire bonding. Okay. But these are the issues that are generally have to be tackled, and these are very engineering oriented problems, because how you manage the heating, the size, the package issues, and then there will be stability issues, by the way. With very high power RF devices, it will tend to oscillate rather than amplify. So you have to look at something called stability of the device. Okay, this stability is an RF stability. Okay, the device, any device such as large as device as this, will start behaving as an oscillator. You do not want that. You want it to behave as an amplifier. Okay, so for instance, if I zoom into that image and we look into individual fingers, then I see that there is something called gate tap. What does a gate tap means? Because your gate fingers are kind of very thin, like gate length, which you call gate length, is very thin. So when you have the gate, the gate length running, and a gate, this is the gate width, but this is the gate length, this is the gate length. So you have thin gates here, and they will take a finite time to propagate. Okay, that's fine. But a thin gate also introduces a lot of gate resistance, and it attenuates the RF signal. So to ensure that the RF signal attenuation does not kill the device, okay, what is that? There is a gate tap every say 100 micrometer. What is a gate tap? Parallel to the gate finger, there will be a thicker finger. Okay, there will be a thicker finger that will carry the gate signal. You have a thicker. When I say thicker, it's a wider line, or you can say it's a laterally wider line, not like in this way. I'm talking about in this way. Okay, so there's a laterally wider line such that your gate attenuation, your signal propagation, attenuation is lower, because it's a wider line. You have a lower resistance. You send the gate signal also along this gate bus, and then it will feed into the gate finger to ensure that the attenuation doesn't happen. Okay, so every 100 micron you will have a gate tap. Gate tap as in a wider signal is bringing the gate signal in parallel, and it's feeding into the actual gate signal to ensure that the attenuation stands at minimum. Okay, so what's happening here is that this will of course lead to a slightly increased dimension of the entire device. So there's always a trade-off, either with cost or with the real estate, the device area, the performance, etc. Okay, And you cannot have this W infinitely large because the signal, this also has to be much lower than lambda by 10. Typically it should be around lambda by 100 or lambda by 200. So the frequency operation will set a limit to the W that you can have, the width of each gate finger. UWG refers to unit gate width. So unit gate width in the previous device was 0.5 micron. So 0.5 micron, 0.5 millimeter, 0.5 micron, correct? Oh, sorry, I'm so sorry, 0.5 millimeter. So the unit width of this gate is 500 micron or 0.5 millimeter. Okay, 0.5 millimeter. So that will be set by the frequency you're having. Okay, as I told you, for a 10 gigahertz signal, if you do lambda by 100, it will turn out to be around 300 micron. So at 10 gigahertz, you will probably have around 150 micron of gate width. At lower frequencies, maybe 1 or 2 gigahertz, you can have 500 micron or 700 micron of each finger. Okay, and then you have to have a lot of them to make a large power cell or a power bar. You can say power bar. All right. So this image I had shown in a previous lecture also long time back. It's basically the inside of a packaged LDMOS, you can say power amplifier. It's not a single device. You can say that there are transistors. This is a transistor. Maybe I can use the red color here. This is a transistor, an LDMOS transistor. It's a very long transistor. This is a transistor, this is a transistor, and then there will be MOS capacitors. You see, this is a MOS capacitor. You can have giant capacitors that are connected in parallel or in series, and then you have inside the package. This is the flange, the bottom of the package, which is grounded internally because you have a P-type sinker in the LDMOS, and this is the drain lead. This is the gate lead, right? These are all these bonding wires. You can see that, right? All the wire bonds that are there. There are a lot of wire bonds. You need just, I told you, you cannot have just single wire. You need many wires. Otherwise, a single wire will create propagation delay, as it feeds into a large manifold. Okay. These wires will also introduce parasitic inductances for sure. Okay. So that has to be modeled, taken into account when you are trying to extract the pad parasitics, or if you're trying to understand the package parasitics. Okay. So if you're doing a matching, sometimes these wires may be used as a part of the matching network. Sometimes you have to de-embed the effect of the wires. It depends on the user and the designer, how they want to have it. So everything has to be very carefully thought out and designed. It cannot be just random. The wire length, the wire diameter, they will determine the wire inductance. So that everything is important. You just cannot put arbitrarily 10 wires or 20 wires of any dimension. Everything is very have to be carefully optimized and understood. Then we come to electromigration. Electromigration is a problem not specific to LDMOS only, but it's specific to any high power device, in this case high power RF device. The problem is whenever you have very high temperature and whenever you have very high electrical current, then you tend to exhibit, or your metals tend to exhibit something called electromigration. In RF power devices like a 50 watt or 100 watt, for instance, a power amplifier die, you are going to get very high current, and that's the reason why your temperature also will be high. A high current will necessarily lead to high temperature. The combination of high temperature and high current will lead to electromigration. So what is electromigration? At very high current levels, at very high temperature I mean 150 degree, 200 degrees Celsius for instance, or even lower, or plus minus around that range, your electrons and metal ions will collide. Okay, your current density is high, so there's a lot of electrons that are flowing in the metal line, lot of electrons, and the electrons and the metal ions will collide. There will be momentum transfer. Momentum will transfer between electrons and metal ions, and there's also heat, correct? So the metal ions will tend to move out. So you can see the metal ions are migrating. So this can either short to metal lines or it can open up to metal lines. Suppose it was these two metal lines are supposed to be parallel lines, but it has gotten shorted, metallic shorted. So this is a short circuit because the metal ions have migrated and shortened it out. Sometimes it may migrate so much it will not short maybe, but it will create a void here. So whatever signal you are feeding in here, an RF signal, will not go to the other side. This side is open. So these are major problems, major reliability concerns. So electromigration is a very serious issue at high currents and high temperature. The reason of this is because of high momentum transfer between the electrons and metal atoms that are colliding at higher temperature and current levels. Okay, it's a wear and tear mechanism. It's just a reliability and wear and tear mechanism. Okay. So the quantifying way is that you use something called MTTF. It's called mean time to failure. Mean time to failure of a device depends on this electromigration a lot. For instance, this is the expression where you have J is the current density. So you see, if your current density is higher, it goes as the square of current density. Please remember, if the current density is higher, your mean time to failure will be lower, which means your device will fail early. it depends exponentially on temperature. If your temperature is higher, this quantity is going to be lower exponentially. So with higher temperature, your mean time to failure reduces exponentially, which is a terrible thing. And the way you define mean time to failure is you define a certain percentage of increase in the line resistance. For instance, you have a metal line, it has a certain resistance R, you will define that if the resistance increased by some delta R percentage, some percentage, I will call that it is a mean time to failure. Now to reach that level, you will take less time if your current levels are higher, if your temperatures are higher. And when you say you take less time, it means the device fails early. Okay. So it is always very important to reduce the current density in each of the metal fingers. You can thicken the metal, so that the current density reduces. You can have wider metal so that the current density reduces, or what happens is that, as actually if you look into the drain, this is the drain and this is the source here, the current is flowing in this direction, so all the electrons are feeding that way, they are increasingly getting more electrons fed in towards this side. So this part is where you will have more probability of electromigration, because electrons are just feeding from side, So this part is the more electromagnetic. So what people do is that there is like a tapered metallic outlet towards the pad. So this tapered increases the width of the metal, right? If you look at the cross section, like it's a cross section like that, but then it's going like that, then it's widening up. So this area will have a larger cross sectional area, so your current density will come down, and if your current density comes down, then your electromigration probability also comes down. Your temperature also, that's something you have to be very careful about, because you have to cool the device and things like that. So people use approaches to reduce the current density. They use a thick metal, for instance, they use a tapered contact like that, they will use wider metal, they will use different metal stacking layers. They also use different, the choice of metal is very important. For instance, copper and gold, they are less prone to electromigration. I mean, the electromigration will happen at much higher temperature or currents. And aluminum copper alloy is also excellent in electromigration, but aluminum metal is terrible. It will electromigrate very easily. So at very slight increase of temperature or temperature and a high current, your aluminum will electromigrate and will short your device. So then you have to use gold and copper, or silver copper alloy and stuff like that. The idea is to reduce the current density and to keep the temperature as low as possible. A higher temperature is always bad for the device. A higher junction temperature is always bad for the device. It reduces not only mobility and performance and things like that, but also leads to serious reliability concerns, such as reduction in the mean time to failure. Okay. Then this is an example of a commercial LDMOS die. Okay, so you can see that this is an 80 watt power transistor LDMOS, and this has 164 gate fingers. This has 164 gate fingers. You can see those are gate taps. You can see those gate taps. But this has 164 gate fingers, and the total gate width is 82 millimeter. That gives 80 watt of power. So the power per unit, gate width is less than 1 watt per millimeter. It's probably like 0.9 something watt per millimeter. Okay, this is from Freescale Semiconductor. This is a 80 watt LDMOS power transistor. I don't know the frequency here. It could be, it has to be less than typically 3.5 gigahertz. Okay, you can see that this, one of them will be the drain pad, one of them will be the gate pad. That's how it is, and the source of course is connected below. This is another commercial device. This is from a company called Amplion. Okay, and just an example. I mean, this company will sell lots of LDMOS RF transistors, but this is just an LDMOS for S-band radar. S-band is 2 to 4 gigahertz. So for 2 to 4 gigahertz radar application, and that becomes strategic, it's an LDMOS device. The power is 115 watt. It's a saturated power typically. Okay, and it's between 3.1 to 3.5 gigahertz. See, and this is a pulsed RF. What it means is that you have your RF signal, which is coming like that, is actually pulsed. Which means you have a pulse, you superimpose a square pulse, and this is to reduce heating. So you will have RF signal, then there's no signal, then RF signal, then no signal, then RF. This is called pulsed RF. The DC will be constant. Sometimes the DC also is pulsed. You need a DC bias and RF, both of them you need, by the way. Okay, it's not only just RF that you are inputting, you also need a DC bias to bias the gate of the transistor or the drain of the transistor. This is an RF, pulsed RF at a frequency of 3.1 to 3.5. at a voltage of 32 volt, which means your breakdown will be around 65 volt or at least 65 volt. You are getting 115 watts at a gain of 14 dB, very good, and an efficiency of, it's a drain efficiency of 49%, which means the output RF power by input RF power is 49%. This is drain efficiency, it says, okay, ND. And these are of course, it says what kind of ruggedness and other things are there. Now you remember this is 115 watt and this is 3.1 to 3.5 gigahertz with an efficiency of 49% and a gain of 14 dB. Okay, it's a gain of 14 dB. Okay, sorry, this is P out of RF by P DC power that you're supplying. Gain is P out by RF by P in by RF. This is your gain. Okay. So now I'll compare that LDMOS with a similar gallium nitride device. Okay. So just to have a feel for the technologies that are available today in the market. Gallium nitride, this is actually 8 gigahertz. So it's not 3.1 to 3. And I mean I can pull up at 3.1 to 3.5 also, but I'm just trying to bring home the point that you get 120 watts of power at 8 gigahertz, which is a more scale device because your gate length has to be scaled down to get power at 8 gigahertz compared to 3.5 gigahertz. So it's an 8 gigahertz 120 watt discrete GaN die. It seems like it's not packaged. These are via holes, by the way. There is no gate tapping here. Okay, and this is one cell, this is one cell, this is one cell. They are all combined here. You see, this is going to give much higher power and all overall performance than a silicon LDMOS or a gallium arsenide. So what are we looking at? We are looking at a small signal gain of 15 dB, power of 120 watt, a drain efficiency of 65%. It depends on the biasing condition, I understand, but it's 65% as opposed to 49% here. The gain is 14 dB here, the gain is 15 dB here. Okay, and we will not care about the intermodulation distortion, but you see the power is more than 115 watt but at higher frequency. Okay, what is the die size now? The die size is 5 millimeter by 0.9 millimeter. Okay, what was this die size? Die size was 2 centimeter by 2 centimeter. So 2 centimeter by 2 centimeter will look like that. This is the die size, and a 0.5 centimeter by 0.5 centimeter by 1 millimeter will look something like maybe something like this, less than that. Okay, something like that, very small. So it's a much smaller footprint. You are going to get higher power at higher frequency with higher gain and higher efficiency. So this is why gallium nitride has been a very emerging and a very promising technology, by the way. Just giving a comparison here. This is the VSWR ratio 10:1. I told you, right? This is the stress up to which the device is going to perform acceptably. You see, at a stress of 10:1 VSWR at 28 volt bias, it's going to give you an output power of 120 watt. Okay, so this 10:1 means that your mismatch in the load and in impedance and the device output impedance is 10:1. In a rough way you can say that, because it depends on gamma, the reflection coefficient also. Anyways, we are talking about LDMOS. So this is another LDMOS from a company called NXP, and they have launched 65 volt LDMOS, which means you can bias the LDMOS at 65 volt. If you can bias the volt it at 65 volt, its breakdown is over 120 or 130 volt, and because of a higher biasing voltage you are going to get more power. Correct, you're going to get more power density, so it means you are going to reduce the number of transistors that you need to combine to get a specific absolute power. Okay, faster development time, design issues, etc., etc. But the thing is, this is only at a lower frequency. So you see 1800 watt or 1.8 kilowatt LDMOS is available, which is biased at 65 volt. However, the frequency is only 1 to 470 megahertz. So it is a sub 1 gigahertz RF transistor, RF power transistor that can give you 1.8 kilowatt of power. It's really large power. Okay, this is the package device you can see, and this is biased at 65 volt. Okay, just remember that. Now these are some aspects of commercial LDMOS devices that I'd like to quickly run through. LDMOS technology or devices is processed in CMOS fab. So of course it's a CMOS compatible process, and they will use 18-inch wafer manufacturing capability, and they will use lithography at 0.14 or 0.13 micron, 130 nanometer node, for instance, as of 2012. It's 10 years back, but things are of course changing. It's getting more and more scale. But just to give you an idea of how it has been, you will use a node, a particular CMOS node, and you will use the CMOS line. So this image on the left shows a schematic of a typical LDMOS device, and this is the shield I told you, the field plate shield that will prevent the gate drain, that reduce the gate drain feedback capacitance. You see the drain has got up and that large, like an L or a gamma shaped, an inverted L shaped large drain. Why? Because this large metal will reduce the current density. Okay, and this current density, you'll reduce the current density. It will help reduce the probability of electromigration, because you have a large gate metal chunk, so it will reduce. However, it will also increase the output probably capacitance, because now it will couple from here to here, but that can be tuned. This dielectric can be much larger, but in general it's a large chunk of metal over there. Okay, You have this sinker, of course, everything is all fine. You can use back metallization. You can use all the, this image you can see there are so many. This is the polysilicon gate here. Can you see that? There is this tungsten shield. Can you see the tungsten shield here? This is the tungsten shield. Then you have so many metal layer, metal 2, metal 3, metal 4, metal 5, etc., etc. You have this interconnects. These are all tungsten plugs, by the way. These are all tungsten plugs that are used to connect different layers of metal. There are different layers of metal, and you use tungsten plug to connect them. These are all the metal. Choice of metal is dictated by the electromigration, reliability, and other concerns. Okay, these are all back end. We call it back end. Anything that happens after the gate, typically these are all the back end of the process. BEOL, people call it BEOL, back end of the line. Multiple layers are used. You can see that they are increasing in generally the width, as they are going up. Can you see that? You are basically taking that signal upwards, thickening the metal, taking it upwards. The top layer is very, very thick. It's 3 micron thick here, 3 to 5 micron probably. And these are the tungsten plugs that are connecting different layers of metal. In between you have dielectric. This is very proprietary. People use a combination of some oxides, some nitrides as dielectric. Okay, this is a 5 metal copper gold LDMOS backend. So you see, aluminum copper, not copper gold. Aluminum copper is a alloy which has good immunity against electromigration. So people use aluminum copper LDMOS backend. You can see this is a scanning electron microscope image of the backend of the process, okay, of an LDMOS, which is a power transistor. This is a more zoomed in image. You can see that this is the shield, the gate field, the field plate, that is the source side coming up here. Okay, people use triple field plate. You see, this is it's called a staircase triple field plate. The first field plate is here, the second field plate is here, the third field plate is here. It helps improve the breakdown because you are reducing the peak electric field here to here to here to here. So the overall area will increase and you get a higher breakdown. This is a triple field plate, all tungsten metal shields. So these are all tungsten. These are all tungsten metal shields. This is a 50 volt LDMOS. So you are able to bias at 50 volt and you are working at a few gigahertz. Okay, so it's a really incredible. You can see that this shade is little different, which is a copper silicide layer on top of polysilicide. Why? Because the polysilicon, so not polysilicide, polysilicon has not so low a resistivity. Its resistivity is reasonable. So to reduce the gate resistance, this is the gate, by the way. This is the gate. Okay, this is the gate. This gate resistance, to reduce the gate resistance, people put a silicide layer on top, like a nickel silicide or a cobalt silicide layer. This helps bring down the overall gate resistance significantly, maybe 5 to 10 times. Okay, and if you lower the gate resistance, the noise figure improves, your cutoff frequency Fmax improves. So it's good. It's good. This is with respect to year, people is showing how the gate length has been shrinking in nanometer, 300 nanometer. They're approaching 200 nanometer at 2012. Now it has gone down even lower, of course. But you can see that people go to all kinds of sophisticated gate drain engineering, such as triple staircase field plate, to enable a high voltage LDMOS at a higher frequency, a few gigahertz. Okay, and you can see that the gate oxide here is tapered. The gate oxide thickness, the gate oxide looks like that. This is the source, this is the drain. The gate oxide from the source to the drain looks like this. Why? Because this is the drain side, the gate, this is the silicon dioxide, suppose. The gate oxide to the drain is larger because this will act like a natural field plate. The gate, the drain side should be, this is precisely the reason why you have field plates. This is one field plate spacing, this is the second field plate spacing, this is the third field plate spacing, but the zero field plate is actually here, where it's like a field plate. You can imagine that this is a gate metal, okay, but your oxide is such that your oxide, this is the silicon surface, the oxide is something like that. So your gate metal comes like that. So this gate metal is further from this side than this side. So this is like a field plate only. Okay, you are adjusting the spacing between the gate metal to the channel in order to mitigate the field effect. So this is like the zero field effect, the zeroth field plate, first field plate, second field plate, third field plate, and then you have a cobalt silicide top layer. So these are all done to improve the performance of the LDMOS. Okay. Now you can see that this is a 30 volt LDMOS that has a snapback at around 90 volt. Okay, and this is a 120 volt device, or 50 volt. This is for a 30 volt LDMOS you need at least 65 volts, so they have a snapback at around 90 volt. Okay, safe enough. For a 50 volt LDMOS you need at least a 100 volt breakdown. They have a snapback at around here, 140 volt, 145 volt, which is safe. So you can see that with higher voltage technologies, your snapback has to be moved further away, and so you need the triple field plate. Now the ruggedness in LDMOS is correlated to the parasitic bipolar. I told you there is a parasitic bipolar action and you want to delay the onset of the parasitic bipolar action so that your snapback is pushed from 30 from a 30 volt to 50 volt, your snapback has to go from 90 volt to 140 volt, 150 volt. So that pushing up the snapback effect has happened. You know, if you have to delay the onset of the NPS transistor. Okay, so you are going to tailor the electric field profile, and that is one of the ways in which you are doing is a triple field plate. They can have staggered field plate, a more inclined tapered field plate. There are many sunken field plate. There are many technologies, but these are all to engineer the field profile so that you can get to a higher device technology. Okay, whenever you have that extra margin between the breakdown and the snapback, so this is your breakdown, this 120 volt is your breakdown, and your snapback is 150 volt. So this 120 to 150 volt is your extra margin that I am talking about here. This extra voltage margin between the breakdown and the snapback, it will allow the device to handle higher drain voltages, which means your drain swing can kind of cross over beyond 120 also, as long as it does not touch 150. So although the breakdown is defined at 120, you are able to have an RF swing that can touch that or exceed that, but for a very low amount of time. Okay, especially in mismatch condition, when you have a high VSWR like a 5:1 or 10:1 kind of a mismatch ratio, when you have a highly mismatched load, you can allow the RF swing to go past the breakdown voltage as long as it does not hit the snapback voltage. So the snapback voltage has to be higher compared to the breakdown voltage, as high as possible, and that's done by the gate drain field engineering such as a triple field plate. This makes the device rugged. This makes the device robust and rugged, reliable 50 volt technology. For reliability, of course, you need electromigration and so many other hot carrier injection, negative bias. There are many things are there in reliability. We are not touching upon that. But the bottom line is that you need a good breakdown to snapback voltage margin. Okay, so that brings us to the conclusion of LDMOS discussion. These are some of the books that I had referred to in this lecture series for LDMOS on RF CMOS devices. Feel free to consult these books as well. So with that, we will conclude today's lecture, and we will go to lecture 42 in the next class, where we will start bipolar devices. Thank you for your time.